Our sun, a celestial body that has captivated humanity since the dawn of time, giver of life, a constant presence in our skies, and the very engine behind every breath we take. It's the source of warmth, the provider of light, and the foundation upon which our planet thrives. Its light embarks on a 150 million kilometer journey to power our weather systems, driving the currents and cloud formations that shape our world, and to fuel the miracle of photosynthesis, the process that sustains nearly all life on Earth. Civilizations have risen and fallen, their calendars and rituals dictated by its rhythms, their fortunes intertwined with its daily journey across the sky. Yet, in our modern lives, we often take its reliability for granted, assuming its constant presence without truly appreciating its power and influence. But beneath its seemingly benign golden glow lies a churning, violent reality, a world of unimaginable energy and constant flux. The sun is in essence a colossal nuclear furnace, a giant fusion reactor burning at millions of degrees. It operates with temperatures and forces that are simply beyond human imagination, a realm of physics pushed to its absolute limits. It's easy to think of it as just a gentle lamp, a comforting source of light and warmth. But it's also a dynamic and at times a volatile star, capable of unleashing tremendous power. Hidden within its depths is a capacity for explosive outbursts, events that can dramatically impact our solar system. These are solar flares. They can unleash torrents of energy and radiation across the vast expanse of the solar system, traveling at incredible speeds. These flares are not mere flickers of light. They are cataclysmic explosions of energy, each one releasing energy equivalent to billions of hydrogen bombs detonating simultaneously. As our reliance on technology grows exponentially, weaving itself into every aspect of our lives, so does our vulnerability to the sun's unpredictable moods, to the whims of its powerful solar activity. Understanding solar flares is not just an academic pursuit, not just science for the sake of knowledge. It's a matter of planetary security, a critical endeavor for protecting our civilization. The story of solar flares is, in a very real sense, our story, the story of humanity. It's a tale of our intricate relationship with our parent star, the source of our existence. So let's journey together to the heart of our solar system and explore these magnificent yet terrifying events. These solar flares. We'll uncover the complex mechanisms that cause them, the underlying physics that drive these eruptions. We'll see how they travel across the vast distances of space. And we'll examine what happens when their immense energy collides with our planet Earth and the consequences that follow. This is not science fiction, a fantastical tale of distant worlds. It's the stark reality of living next to a star, a powerful and dynamic force that shapes our existence. The sun gives us life, sustains us, and provides the very foundation for our civilization. But its hidden danger, its capacity for explosive outbursts, commands our respect and demands our attention. Ultimately, our survival, our continued prosperity depends on understanding and preparing for its awesome power, for the forces that shape our solar environment. Imagine witnessing the sun, our life-giving star, up close and personal. What you'd see isn't the serene, constant orb we perceive from Earth. Instead, it's a roiling ocean of plasma, a sea of superheated gas constantly in motion. The photosphere, the sun's visible surface that we can observe, is a dynamic canvas of boiling motion, a testament to the immense energy churning beneath. Look closer and you'll see granules, each one a bubbling cell of plasma, and each granule is roughly the size of a country here on Earth. Towering above this turbulent surface are great loops of incandescent material called prominences. These prominences arch majestically into space, their shapes sculpted by invisible, yet immensely powerful magnetic forces. They dance across the solar landscape. And from this ever-changing turbulent surface, solar flares are born. These flares are sudden, incredibly intense releases of energy, the sun's way of momentarily unleashing its raw power. Think of a flare as a cosmic lightning flash, a sudden burst of light and energy, but vastly, almost incomprehensibly, more powerful than any lightning we experience on Earth. In a matter of minutes, the plasma within a flare heats to tens of millions of degrees, far hotter than the sun's core. This extreme heating unleashes a torrent of radiation across the entire electromagnetic spectrum, starting with radio waves and extending all the way up to the most energetic form of light, gamma rays. These solar flares are not random chaotic events. Instead, they're driven by the sun's complex, ever-changing magnetic fields, the invisible forces that govern so much of its behavior. The sun, in essence, is a gigantic magnetic dynamo, a colossal engine generating magnetic fields on a scale we can barely imagine. And this internal magnetism is what shapes everything we see on the sun's surface, from the constant stream of the solar wind to the very nature of planetary weather throughout our solar system. Solar flares, therefore, are more than just storms. They represent a fundamental reconfiguration of cosmic energy, not just surface-level disturbances, but deep transformations within the sun's magnetic architecture. The energy that fuels these flares builds up over days, sometimes even weeks, as magnetic fields twist and become increasingly strained. And then, when the tension becomes too great, it erupts violently, releasing its pent-up power in a sudden explosive flare. So, to truly understand the potential threat and the sheer beauty, we must first understand the sun's complex, tangled magnetic field. It is the true engine driving this celestial drama, the source of both the sun's beauty and its potential fury. And it is here, on the surface of our star, that the real story of solar flares truly begins to unfold. Deep within the sun's core, a realm of unimaginable pressure and heat, nuclear fusion relentlessly powers a vast ocean of plasma, a superheated state of matter where electrons are stripped from atoms. This intense activity sets charged particles in constant turbulent motion, creating a dynamic environment. This movement generates powerful electrical currents that flow throughout the sun's interior, like rivers of energy. These electrical currents, in turn, give rise to complex and ever-changing magnetic fields. This self-sustaining process of magnetic field generation is called the solar dynamo. Unlike the stable field of a simple bar magnet, the sun's magnetism is inherently chaotic and unpredictable, intricately shaped by its differential rotation, a phenomenon where the equator spins significantly faster than the polar regions. This difference in rotational speed causes a constant twisting and shearing of the magnetic field lines, tangling them into complex knots. This process results in the storage of immense amounts of magnetic energy within the solar atmosphere. Over the course of the sun's approximately 11-year cycle of activity, these tangled magnetic field lines become increasingly knotted and strained, reaching a point of instability. Eventually, the stressed and tangled fields rise buoyantly to the sun's visible surface, the photosphere. This creates active regions, characterized by intense magnetic activity, often marked by the appearance of sunspots. Within these active regions, the conditions are ripe for the occurrence of powerful solar flares, explosive releases of energy triggered as the sun's magnetic field lines violently snap and reconnect. The process of magnetic reconnection is absolutely key to understanding these events. When oppositely directed magnetic field lines are forced together, they merge, rapidly unleashing the stored magnetic energy. This energy is released in a spectacular burst of radiation and particles. The released energy rapidly heats the surrounding plasma to millions of degrees and accelerates particles to near light speed. These particles are accelerated to phenomenal speeds, contributing to the solar wind. The sun's magnetic heartbeat, its rhythmic cycle of magnetic field tangling, stressing, snapping, and reconnecting, fundamentally dictates the overall rhythm and intensity of solar activity. These powerful, localized explosions broadcast vast amounts of energy and radiation outwards into space, permeating the entire solar system with their influence. Our own planet Earth is constantly within reach, and therefore subject to the effects of this dynamic and powerful magnetic force. When the sun's tangled magnetic fields break through the surface, they create sunspots, dark, cooler patches on the sun. Sunspots aren't cold, just cooler than their surroundings, thanks to intense magnetic fields thousands of times stronger than Earth's. These regions are the primary sites of solar flares and eruptions. Sunspot groups, with their complex magnetic polarities, are cosmic powder kegs, where energy builds up. The more tangled the sunspot group, the greater the potential for a massive energy release. Coronal loops arch above sunspots, glowing with superheated plasma, a visual sign of stored magnetic energy. When conditions are right, magnetic reconnection triggers a solar flare, unleashing energy in a blinding flash. Sunspots are not passive, they're portals through which the sun's internal power erupts. These are the focal points for the most violent events in our solar system. Watching sunspots is watching the sun's power in action. When a solar flare erupts, it launches a multi-stage assault on Earth. First comes electromagnetic radiation. X-rays, UV and radio waves, arriving in just over 8 minutes. There's no warning. The impact is immediate, disrupting the upper atmosphere. Next, energetic particles, protons and electrons, race toward Earth, arriving within an hour, posing radiation risks to satellites and astronauts. The most powerful flares often unleash a coronal mass ejection, or CME, a billion-ton cloud of magnetized plasma. Unlike a flash of light, a CME is a tangible, massive cloud, taking 1 to 4 days to reach Earth. When a CME is aimed at us, it's the greatest threat to our technology, capable of inducing devastating electrical currents. The arrival of a CME is the final, most impactful stage, a cosmic cannonball that can trigger catastrophic blackouts. Our modern world is more vulnerable than ever to these solar assaults. The first impact of a solar flare is felt high in Earth's atmosphere. X-rays and UV radiation slam into the ionosphere, causing radio blackouts on the sunlit side of Earth. High-frequency radio communications, vital for airlines and emergency services, can be disrupted instantly. Next, solar energetic particles threaten satellites and astronauts, damaging electronics and posing radiation risks. The greatest danger comes from a CME slamming into Earth's magnetic field, triggering a geomagnetic storm. This storm induces powerful currents in power lines and pipelines, currents our grids aren't designed to handle. Transformers can overheat and fail, leading to cascading blackouts across continents. Recovery could take months or years, plunging society into darkness. The invisible threat from the sun can bring our world to a standstill. We're not helpless against the sun's fury. Space weather forecasting is our first line of defense, with spacecraft like NASA's Solar Dynamics Observatory watching the sun for warning signs. Satellites at Lagrange Point 1 act as cosmic tripwires, giving us precious lead time before a solar storm hits. This warning allows grid operators to take protective measures, reducing load, isolating parts of the grid, and preparing for impact. Engineers are hardening infrastructure, designing transformers to withstand geomagnetic currents and installing blocking devices. Satellites are being built with better shielding and can be put into safe mode during storms. It's a multi-layered strategy: prediction, mitigation and engineering. We're learning to live with our star, building a technological shield to protect our way of life. The sun's activity ebbs and flows in an 11-year solar cycle. We're now in solar cycle 25, heading toward a more active peak than expected. This heightened activity increases risk, but also opportunity for science. Missions like the Parker Solar Probe and Solar Orbiter are gathering unprecedented data, revolutionizing our understanding of the sun. The goal? Move from forecasting to true prediction, knowing exactly when and how big a solar eruption will be. This requires deeper knowledge of magnetic reconnection and solar physics, a grand challenge for astrophysics. As we plan missions to the Moon and Mars, protecting astronauts from solar storms becomes critical. Our technological world's vulnerability makes solar research more urgent than ever. From ancient worship to modern science, humanity has always been captivated by the sun. It's our anchor and our energy source, but also a partner with a tempestuous side. The same star that sustains us can unleash storms powerful enough to cripple our civilization. Understanding solar flares is essential for protecting our interconnected world. A major solar event could disrupt everything from power to healthcare and finance. Science and engineering are our tools for resilience, allowing us to confront and adapt to cosmic challenges. We're no longer passive observers. We're active participants, building knowledge and defenses. Our dance with the sun is one of dependence, respect, and vigilance. By understanding our star, we secure our future in its brilliant, eternal glow.